Hello, my name is Graham Wood and I'm here to talk to you today about database time-based performance tuning from theory to practice. I've been at Oracle for quite a long time now, and most of my time has been spent doing performance-related work. I was the architect for many of the things that we'll be talking about in this session. I currently work in the real-world performance group. The real-world performance group, we spend a lot of our time trying to get customers to focus on getting to the root cause of their problems rather than trying to deal with symptoms of performance problems, which is a common error that we see. The three most common root causes that we see in our customer engagements are folks not using the database the way that it was designed to be used, suboptimal architectures, and thirdly, suboptimal algorithms in the database. So things that turn into database bugs once we've investigated them. Way less of those than there are of the first two. So our agenda for this session, I'll be talking about database time and its sibling average active sessions, then about the database time method, and lastly about tools and maybe some of the things that you aren't aware that have been introduced more recently in terms of use of database time. So starting with database time and average active sessions. So first of all, why do we care about time? Well, when it comes down to it, all of performance is really about time, and it's only about time. Obviously, there's lots of cliches about time is money, but essentially, when a customer is using a system, when a user is waiting for the database to do its operation, we're talking about time. And if we make the database come back faster, if those operations take place more quickly, then we've reduced the time that something is taking to happen, and we've increased its performance. So this session is about database time. We specifically came up with the name database time to differentiate it and to make it clear what we were dealing with here. And because we came up with the term, we also got to define it. And as part of defining it, we were very careful about what was included and what wasn't included in this term. So database time is the time for foreground sessions in database calls. So it's the time that a session spends from the time a call comes in from the user to the time that the response returns to the user. And these days, sometimes it's a user, more often it's a middle tier. But it's the time spent within the database doing operations for a foreground session. That includes CPU time, obviously. It also includes time spent doing IOs, and it also includes what we refer to as non-idle waits. The absolutely standard idle wait that we see sessions waiting on a lot is SQLnet message from client, which is basically a database session that is waiting for work to do from the user. So non-idle waits are things like contention waits, so lock waits, latch waits, waiting for some resource or other. So all of those are part of database time. And as I say, we specifically came up with the name database time and didn't call it response time, because from the description that I've given you so far, you can probably think that, well, okay, so this is the database response time. But response time is a hugely overloaded term, and network guys talk about response time, storage guys talk about response time, and they're all talking about different things. So we made a point of coming up with a different term because that way it disambiguates the whole thing. And the intention with database time was that this becomes a common currency for all Oracle performance analysis. So any part of the database, any instrumentation in the database, we try to focus on how much time things cost so that we can easily look at where there's the biggest benefits to be gained by performance tuning. So if we look at a simple example, here we have a user connected to the database, and this is something like a transaction of buying a book from Amazon. And so the user starts off, they're browsing through books. Part of browsing through books is the time spent in the database. And in this diagram, the little green blocks under the timeline there represent the time spent in the database. So after they've maybe found a book that they're interested in, they then go and read reviews. So that's more calls to the database, pulling back the review information. After they've read the reviews, they decide they want the book, so they add it to their cart, more operations against the database, and finally they check out. So we can see that the entire length of the black line there represents the wall clock time, elapsed time for the session, and the blocks of green represent the time spent in database calls. So those represent database time. So a couple more concepts. Talked about database time foreground sessions spent in database calls. We have active sessions, and an active session is a session that is currently in a database call. So within one of these green blocks of time here, this is an active session. And we also have another term that we see in some of the Enterprise Manager screens, which is called the average activity of the session, percent active. And this is the ratio of wall clock time, of database time rather, to wall clock time. So in this case, if you just eyeball that, and it looks like there's maybe 60% of the time here is spent in the database in this example. So here we see a screenshot of the way that average active sessions, database time appears in the monitoring tools. So here we have the activity of a single session over time. Our y-axis here is percentage activity. And we can see we have big stacks of blue, and the blue goes up to 100%. So these are periods of time when the session is entirely within database calls. There's no communication between the user or between the database and the application tier. So we can see that this session was spending large majority of its time in the database and taking several seconds, in fact in this case several minutes at a time in some of these database calls. What happens when we build up on this? So going beyond one user, we now go to multiple sessions in the database. Well, we could draw each of these sessions in the same way that we drew our single session and put in their blocks of database time. And so we could draw each session separately. If we now take a point in time and look at which sessions are active, that's our number for average active sessions. Right? So at point T here, we have 2 sessions that are active because our line is crossing 2 green blocks. How do we visualize this, particularly in an Enterprise Manager? Well, we could draw all of these lines separately for each user, but then for large systems you'd have many thousands of these and it wouldn't really work very well. So what we do is effectively play Tetris with those blocks, and we shuffle them all down and stack them up, and what you end up with is a graph of average sessions over time. And how does that look in Enterprise Manager? It looks like this, and those of you who've used Enterprise Manager and the main performance page and top activity page will recognize this. So this is showing how many sessions are active at any point in time. And there's additional information in there because the color of the graph is filled in with indicates what sort of activity the database session is doing. So two of the most prominent ones here, green is always CPU, blue is always I/O. Right, so we can see that there's periods when there's a lot of sessions doing I/O in this case. And the way that we talk about using these performance pages for doing analysis, diagnosis, is click on the big stuff. That's where all the database time is being spent. And remember, we're trying to improve performance, which is reducing database time. We can reduce database time much more effectively if we look at where there's big chunks of it. So average active sessions. Average active sessions is actually the total database time divided by the elapsed time. And you can think of it as the number of full-time equivalent sessions that could perform that same amount of work. It's very common for us to see systems that have several thousand sessions connected to the database, and average active sessions is of the order of 30 or 40 at any point in time. That means that the entire workload for that system could be performed by as few as 30 or 40 sessions. And average active sessions has one additional benefit in that we can compare it across systems. So if a database has an average active session value of 50, then it's doing more work than one with average active sessions of 30. So you can think of this as being the load on the database at any point in time. So what happens with database time as we vary the system? Well, if we add more users to the system, and so we're doing more work, then there's more calls, so database time increases. If we modify the application and add more logic into the calls, more SQL calls to the database, then we're making the transactions larger, calls take longer, and database time increases. If we have system issues, so if our I/O performance degrades because the storage subsystem is overloaded, for example, then our I/O time will increase and database time will increase. And if we have application performance degradations, so if we run into locking issues between multiple users on the system, then again, our database time increases. One particular case that I'd like to highlight here is where we have a situation where the host is actually out of horsepower. So we have a CPU-bound host. CPU is a constrained resource, and so you're never going to see huge amounts of weights on CPU. Right? That's not how systems instrument or are instrumented. So what happens when we have a CPU-bound system is that the foregrounds will be sitting in the run queue of the database server. If they're within a wait event at that point, then the length of time that wait event takes according to the database will be artificially inflated. Right? So your I/O, instead of taking 5 milliseconds, may be reported as taking 15 milliseconds if you're spending 10 milliseconds on the run queue. So in fact, we have a little graphic for that. So here we have a user session that is doing some I/Os, so it does a blue I/O. The actual time that it takes for the I/O to complete is represented by the blue. But then this is on a system that is CPU bound, and for that wait event to be completed within the database code, our process has to get onto the CPU and so it has to sit in the run queue. So by the time we get to running the code that completes the wait event, we now have a recorded wait time which is significantly higher. So, so what this means is that all of the wait events show up as being very high numbers when we have a CPU-bound system. And so here's an example, a performance screen from a system. Now, if you were to, first of all, do an initial look at this screen, you would see that in the top activity screen, in the main performance chart there, that there is this very large block of blue, and it looks like this is an I/O problem that we have. If you look below it, however, you'll see that we're not actually doing any more I/Os at this time. And if you look above where we have the host information, you will see that for this period of time where we have the large block of blue, that the load on the database server was very high. So this was CPU bound, and so each of those I/Os were artificially inflated. So this looks like an I/O problem, even though it's CPU. You can see that the green there that represents CPU isn't a major part of this display. So that's one thing to watch out for, that if you're CPU bound, you always need to tune for CPU first, and you need to be wary of misinterpreting the information about which of the wait classes is the root cause of the problems on the system. So, where do we find database time? Well, there's a number of views within the database that contain database time. Time model views, both system and session. We actually have a stat in there called DB time. Right? So that's very easy to find. In sysmetric history, we actually have a couple of different metrics that you can use. There is database time per second, and there's also CPU usage per second, which is very useful if you're trying to identify that you're CPU bound. And in 11G and above, we actually have a metric called average active sessions. So this is the same thing, same value that you would see at any point on the main performance screen or on top activity screen. In $SQL, we have a column there called elapsed time, which isn't actually elapsed time. It's actually database time. That was put into $SQL back in Oracle version 9 time frame, so before we had the concept of database time. But the value that is shown in elapsed time is actually the database time that a SQL statement took, not its wall clock elapsed time. Also in $SQL, we have information about how much time was spent in various weight classes as well. So one of the issues that we used to run into a lot was where there was a big difference between elapsed time and CPU time for a SQL. We didn't know if that time had been spent waiting for application issues, things like row locks, if it had been spent waiting for concurrency wait events like latches, or if it had been waiting for I/Os. So by having those wait class metrics in there, just looking at an individual SQL, we can see what constituted the main proportion of its time in $SQL. And last but not least, we have $active session history, commonly referred to as ASH, which contains very detailed information about where the DB time on a system is spent. As opposed to most of the information in the instrumentation in the database, which is accounted information. So, we capture the time that something started, we capture the time that something finished, and do a delta between those and record that time, or we maintain counts, things like that. Active session history is rather different in that it is sampled information. So once per second, we sample information about all of the sessions that are active in the database. So remember the definition of an active session. It's one that's in a database call. And we sample a very large number of pieces of information about what that session is doing. We actually, although only foregrounds are part of database time, we actually sample backgrounds as well, because that can help us with doing some of our diagnosis. The 1 second samples go into an in-memory buffer, which can be viewed by looking at $$ active session history. And when we take an AWR snapshot, we take 10-second samples. So we take like 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, 60 seconds, and take those, put them into an on-disk structure so that we can look at longer-term history. And those numbers, the 1 second and 10 second, have worked very well for us since this has been available, which is pretty good, seeing as we came up with them by putting a finger in the air and think, yeah, that should probably work. But what ASH does is it gives us a very good idea of the database activity over time, and allows us to get into really quite a lot of detail about the activity in the database. How do we use ASH? Well, the simplest ASH math is count star equals db time. So basically, we count up the number of samples that we have in ASH, and we say that each sample, each row in a sample, represents 1 second of database time, because we're sampling at 1 second intervals. So for in-memory, count star equals database time. And then we will typically use one of the other pieces of information that's in there to do grouping. So if we want to find the top SQL for a period of time, then we will group by a SQL ID. If we want to find which sessions have been most active, we will group by session ID. So ASH is this very big fact table, and we use all of the dimensions that are available to do drill downs in different dimensions. When we're doing the in-memory, count star is db time. If we're going against the on-disk structure, which is DBA hist active ses history, we ran out of characters for that one, so session got truncated. There we have to take count star and multiply it by 10 to get the database time. Here's an example of how to use it. What we're doing here is we're looking to find out what was the top SQL for the last minute on this system. You can see that we're looking for sysdate -1 over 24 over 60. We're removing the background records by eliminating those based on session type, and then we're grouping by SQL ID. So this then tells us which SQL statements have done the most work in the database in the last minute. So if we were to run that query, we'd get something like this. And we can see that the top SQL statement there has a db time of 60, which means it's taken 60 seconds of database time in that last minute. Now that may mean that one execution of that SQL statement was active for the entire 1 minute period that we were looking at, or it could mean that there were 60 different executions of this, each of which were seen in different ASH samples. Right? We can't tell that from the information that we have here, but we do know that SQL ID was over 60% of the load on this system. Okay, so if we look at a graph of database time over time, we have the area under the curve is database time. If we were to draw ASH samples in as a histogram underneath that curve, then at any point in time, the height of the curve is the number of samples that we would have in the ASH records for that 1 second period. So ASH is very different in that it's sampled rather than accounted. So how does it compare to the accounted information? So what we have here is the top graph shows information from the top activity screen, which is entirely sourced from ASH data. The lower screen, the lower graph shows information from the perf page, which is sourced from Sysmetric, which is accounted information. And you can see how closely these two completely separate sources of information tie up. One thing that I will highlight is that the granularity of active session history, so 1 second samples, and when we're displaying in Enterprise Manager, we will typically do aggregation across 15-second samples, means that things like peaks don't get as averaged down as they do in the accounted information, which is only collected once every minute. So you can see that where there are peaks, the peaks are higher in the top graph than in the lower one. And particularly in terms of the CPU usage there, you can see that that's very clearly higher in the upper case. But overall, the shape of this really mirrors the accounted information that we have. So that's database time. Where do we use it? Well, the reason that database time was created was in order that we could write ADDM. And ADDM is the Automatic Database Diagnostic Monitor. What ADDM does is it analyzes data from AWR, Automatic Workload Repository, and it highlights where the bulk of the time is going. So the idea of having database time as this common currency for all performance work was so that it would allow us to automate the diagnosis of performance problems on a system. Right? So whenever you take an AWR snapshot, ADDM will run automatically. It will run through the data for that new snapshot, compare it to the previous one, and it will highlight where the bulk of the time is going, and in some occasions it will tell you what you can do to improve the performance in that area. We've already seen that database time is used in the performance page and the drill downs, top activity. Number of the other reports use it. So the ASH report has database time up at the top of the report. AWR and the new AWR warehouse also prominently display database time, as does SQL Monitor, which is the preferred tool these days for doing investigation into the performance of individual SQL statements, and the new Perf Hub, which is available with EM12. All of these things use database time. So I say these things use database time. How do you use database time as part of a method for improving performance? Well, the short course for how to tune using database time is work out where the time is being spent and reduce it. The even shorter course is you ask Adam, because Adam was designed and developed to do exactly that. It does a database time-based analysis of the last period for AWR and makes diagnosis and recommendations for how to improve the performance. But if you're trying to do this manually, let's put something more like a regular method about this. And many of the things that are as part of this method are, well, how can I say this? They're really non-technical. A lot of these things are things that the computer can't do for you. Let's start with identifying performance problems. No matter how much instrumentation we put in the database, it's still the case that the main way that DBAs find out about performance problems is that users call them up and say, system's going slow, is there a problem? So first of all, identifying that you've got a problem is a key thing to do. The next two parts of this method are the ones that we very often see being omitted. First one is to scope the issue. So how many of the users on the system are affected by this problem? Is it just one user that's having a problem? Or is it just that that's the first user that has called you, and as soon as you put the phone down from that user, there's going to be somebody else on the phone also complaining about performance? So there's a number of different scopes. It can be down to an individual user. It can be an individual application running against the database. It can be a database instance within a rack system, or it can be the entire database. Right? So knowing which of those scopes you're dealing with is very important, particularly when it comes to trying to fix the problem. Once you know how big the problem is, the next one, setting goals, is really one that comes about particularly in things like consulting engagements, where you need an exit clause, right? When am I done? So that you don't suffer from what is in term compulsive tuning disorder. There's the stage at which you stop actually trying to tweak the system. What is acceptable for the system? Now, often those goals, people try and set very high level goals like, oh, all operations on the system should take less than 2 seconds. Well, I have to tell you, if you're going to be modifying 1 million rows in the database, it's probably not going to happen in 2 seconds. Right? So what I try to do is get customers to establish goals which are much more related to the business than to the technology. So goals like, oh, well, we have to be able to take 100,000 orders a day, or 10,000 orders an hour. We don't want checkout to take longer than 2 seconds. And that's a much more reasonable time-based goal. Now, most methods at this stage, you would then set out to capture more information from the database about what it's doing. In the case of the DBTime method, one of our main concerns with developing the manageability infrastructure was to make sure that it was sufficiently low overhead that this data capture was on all of the time. So the very first time that you have a problem on a system, that data is already being captured for you as the problem occurs. So data capture in the database time method is, in the majority of cases, a no-op. So once you've got the data to analyze, so we have our AWR data, we have our Ash data, it's all then down to analyzing where the time is being spent and where the biggest potentials for improvement are. And that's the part of it that we were really keen to automate with ADDM. Now you get to the part where I'd like to see DBAs spending their time, which is working on coming up with solutions for improving the system on the basis that you've got a good diagnosis of what the root cause of the problem is. And so coming up with recommendations for how to modify the system to reduce the total database time is to me, that's the hard bit, right? That's where people need to be thinking about what they're doing and coming up with good solutions. Once you have a potential solution, putting the solution in place, and then never forgetting that you need to evaluate how that solution does against the goals that you'd set earlier in the method. If you still haven't met your goals, well, did the changes that you make meet the goals that you'd set for those individual changes, or did they not make any difference? If they didn't make any difference, I would strongly recommend that you actually back them out. We often see customers who get wedded to what they think is the solution for the problem, so that even if they put it in and it makes no difference, they say, oh well, it's probably not causing any problem, so we might as well leave it there. If it was meant to fix a problem and it didn't fix it, back it out. And then you need to come up with something else to try. So, but hopefully when you get down to the end there, you put in your solution, evaluate it against your goals, meet your goals, and you're good to go. You're finished. So that's the database time method. Very simple, and it's really all about being numeric about things. So what we used to see is customers spending a lot of time arguing about what the problem was and using strength of character and loudness of voice as a way to determine what the biggest problems were in the system. Using the database time method, there's numeric values there that clearly tell you where the problem lies in the system. Okay, so when you're investigating database time distribution, depending on the scope that you're looking at, you will be looking in different places. If you're looking at individual sessions, for example, you will probably be looking at ASH data because the AWR data averaged out over all of the system is unlikely to be showing you enough information about what an individual session is doing. Okay, so here's a sample of a top activity screen, and we can see that the grey slider is over a 5-minute period where there was a blip in performance, and we can see it's partly CPU, partly disk I/O. There's lots of green and blue there. Right, so if we were looking at this 1 hour period, this would be one of the 2 periods that we would be interested in looking at. Right? When we look at the information in the lower part of the screen, it actually tells us details about what was happening in that 5-minute period represented by the grey slider. So here we can see that both on the top sessions and on top SQL, we have sessions and SQL that were doing large amounts of work. Now the one on the SQL side is particularly interesting. Most of the SQL that is coming up as being high load is actually I/O bound. So we see lots of blue there. We know that for this period of time, we were actually trying to utilize more CPU than we had on the machine. And so we're looking here at where the CPU is going, and that top SQL is consuming a very large percentage of the CPU during this time period. Right, so it's very easy to identify problem there using the top activity screen. When we're modifying the system, a couple of important points here. We know that the important thing is to reduce the amount of database time. So making sure that we are addressing the things that represent the largest amounts of database time first is a key point, and making sure that we're addressing root causes, not just symptoms. And classic example of that is on systems that are CPU bound. we will often see latches and mutexes coming up as the top wait events. Right? Those are symptoms of the fact that we're CPU bound. They're not the root cause. Right? So making sure you're dealing with the root cause. Avoiding scope mismatch. And again, the classic example here is where we run into a situation where there's a SQL statement that is consuming lots of time. We maybe investigate what to do with it, maybe talk to support. They can say, oh, well, there's an underscore parameter that might give you the right plan for that. So we then put the underscore parameter into the init.aura. Now, changing the init.aura potentially affects every SQL statement on the system, when what we were trying to tune was a single SQL statement. So that's what I mean by scope mismatch. We had a problem that was one SQL wide, and we were applying a solution that was database wide. So key point in making modifications is that you try and, as closely as possible, match the scope of the solution with the scope of the problem. Good experimental practice, always try and apply one change at a time. Yes, I know it's hard, and that often time pressures will mean that you have to apply more than one change in a single test. When you are doing that, at least make sure that you can separately identify the result of each of the changes that you've made. We often run into users who have made several changes on the system. They had some benefit, but they don't know which of the changes it was that gave them that benefit, so they don't know which things they can back out and which things they should leave in. Validating your changes, so measuring as you get your changes in, and then stopping when you've met your goals. So as a consultant, that was, okay, that means I can pack my bags and go home. Certainly avoiding the compulsive tuning disorder is key there. So, database time method, what are its advantages? Well, for me, the key thing is that it's working with the only thing that really affects users, which is time. It's focused entirely on the time spent in the system. It has the advantage that it's working with data that is always on, so there is no requirement to be able to reproduce a problem before you can successfully diagnose it. And because it's dealing with this diagnostic information that is always there, we can make it numeric, we can use scientific methods. It's not like in the early days of Oracle performance tuning. You know, it seemed like you would have to have some guy with a big pointy hat come in and do incantations over your database. Right? We've moved away from that. So now we have all of the information there to be able to diagnose and determine what the problem is in the system. And this method works for pretty much any of the problems that you can see in your database. In particular, if you have a locking problem, if you were doing session-based tuning and tracing an individual session, the issue there is that you can see what the session had as a problem. It was waiting for a lock, but you don't have any information about the other session that was blocking it, and so then you have to go, typically would have to go around more iterations before you can find out what the real root cause of the problem was. All right. And so database time method is all about getting the system to do the same work, the same load in less time, which is a definition of performance improvement. Okay, so let's move on to the last section. We'll talk briefly about some of the tools that are out there that use database time. So many of you, I'm sure, are familiar with AWR. The AWR report has been around from 10G, and prior to that there were StatsPack reports, which is pretty similar in content to AWR. The AWR report has database time up on the front page there, and a number of the things that it does, that it shows, are breakdowns in terms of database time. When you go on to using AWR on a 12c database, one of the things that we've done there is we've included the ADDM recommendations and summary up at the top of the AWR report. The reason for this is very simple. I often got requests from people saying, well, could you analyze this AWR report? My normal response was, well, ADDM already did an analysis, so how about you show me what ADDM came up with? Because in large majority of cases, it's going to have identified the problem on a system. So in order to shortcut those extra dialogues, in 12c we actually have the ADDM findings up at the top of the AWR report. So that will make some of those interactions rather faster with support as well. So ADDM isn't just a single report. These days there are now a number of different levels of ADDM. So the initial ADDM was for a database instance. There is a database-wide, so across all of the instances of a rack. And there is now what is referred to as real-time ADDM that will allow you to look at things that are happening at the current time. So, but ADDM is entirely based on doing analysis and making recommendations based on database time. Okay, so these are some screenshots, and you can see ADDM findings are listed in order of the amount of impact that they have. So over on the left-hand side of the screen shows the impact there. That's actually the database time for that finding. And don't be concerned that those add up to a lot more than 100%, because the findings here are not completely orthogonal. So in this case we have top SQL up at the top, and the next one is top SQL by I/O. Well, obviously some of the time spent doing SQL is also the time spent doing I/O. So don't expect these to add up to a total of 100%. When we drill down, we can see that the recommendations that we get also indicate how much database time we would hope that doing the particular action is going to save. Now for a SQL, and tuning a SQL, that's kind of hard to guess. So I think we just assume that you're going to be able to make it run 100% faster, so taking no time at all. If you're looking at shorter periods of time, you're looking at transient problems, then we've seen some screens previously from the real-time interface of Enterprise Manager. And so the technique here is the click on the big stuff, right? So here we have a large blip of green, and in fact it's the light green, which means we were hitting scheduler limits. So the resource manager was actually limiting the operations on the database at this time. And then we can drill down into seeing what exactly was the cause of that being CPU bound during that time. Again, here we can clearly see that there was one of the SQL statements that was consuming a lot of the CPU in this case. And actually in this case, as we drill down into that individual SQL, we can see that there were 2 copies of this SQL statement that were actually being run by the same user. And so this was one of those cases where a user was running a slow SQL, the SQL didn't come back, because the user was just running in a browser window, all they had to do was just close that browser window, start the application again, and start the query again. And so now you've just doubled the load on the system. And in this case, that was exactly what had happened. The user had aborted, or thought they'd aborted, their initial execution and started a second execution. Okay, so we can drill down using the information in the plan, and we can see that this plan has some very high CPU costs in there. Okay, something rather different in terms of using database time is the grid control database load map. So this allows us to see a comparison of all of the databases that are being managed by one enterprise manager and see which of those databases has the highest load. So I talked earlier about average active sessions and how this is comparable across different systems, or fungible as we sometimes term it. And that's what we're doing here. We're looking at the load across hundreds of different systems and seeing which ones are doing the most workload, because those are probably the ones that we're going to have DBAs spend time monitoring and investigating. The previous slide, we were looking at this just at the database level. We can then drill down into individual database instances. And the colors that we have here represent the predominant wait events. So either green for CPU, blue for I/O, or the kind of orangey color represents other weights there. Azure Analytics, which is new with EM12C, allows us to do the same operations that we could do with the top activity screen in Enterprise Manager, but we can now do rather more in terms of detailed analysis. The key thing for me is that we can actually finally change the size of the slider. So that 5-minute slider that we had in the top activity screen, we can now change the time, and we can now really focus on a particular period of interest on the system. And we can do a lot more in terms of varying the analysis that we do and filtering some of the operations out. So we can really get right down into great detail using Azure Analytics. I'll also mention the AWR warehouse, which now allows us to pull data together from lots of different databases. So the original AWR was always in the production database. Obviously, if you're going to be looking at long-term trends, you don't want to be looking at a year's worth of AWR data on the production database itself, right? That's not good use of the power of the production system. You want that to be running the business. What AWR Warehouse allows you to do is to pull AWR data from lots of different databases and do either long-term trending analysis on the warehouse, or do compare and contrast between different databases. So for example, if you have a number of deployments of the same application, you can do a compare and contrast between those, see which ones are running well, why they're running well, what changes you can put into the ones that aren't running as nicely. Okay, and SQL Monitor here. So the SQL Monitor screens, SQL Monitor really is the tool of choice for doing SQL level investigations into database performance. It will show you the recently executed SQL statements that have taken a significant amount of time in the system, and then you can drill down into individual SQL statements, and you can look at which of the individual plan lines in the SQL statement were consuming the database time. So here we can see that where the CPU resource was being used in terms of individual plan lines, and that's really a very powerful way for diagnosing what was the problem with a SQL statement. Right? SQL Monitor is an excellent, relatively new diagnosis tool for individual SQL statements. Okay, so that's the end of the presentation. So I've been talking about database time, which is a combination of instrumentation and reporting that allows you to do performance diagnostics across many different scopes, allows you to take a numerical approach to doing your performance diagnosis. And what I've been talking about, the way that the database is instrumented, one of the other key things is that as new features go into the database, we also instrument them for database time. So one of the new things with database 12.1 is database in memory, and that has already been instrumented so that we can do DB time-based analysis on using that. So, over time, as new features come in, they all get incorporated into the database time. Okay, so thank you very much for your time, and I hope you've got something out of this session, and good luck with using database time-based analysis. Thank you.